The reason that the dot product turns out to be so important on Rn is because the dot product tells us a lot about the geometry of Rn in a pretty familiar way, right? So for the dot product, if you dot a vector with itself, then the square root of that gives you the length of the vector. So I guess I should write it like this. Square root of v dot v is actually the length of that vector in Rn. Also, the dot product in Rn tells us about geometry because we know that the dot product of v and w is actually the length of v times the length of w times the cosine of the angle between them. And then finally, another reason why we like the dot product is because we can tell if two vectors are orthogonal in a quick and easy way just by checking if the dot product of the two vectors is 0. We would, now that we have the idea of inner products in other vector spaces, we might hope to generalize these facts, but there's actually a problem, which is in other vector spaces, there's not usually any obvious notion of what it would mean for what we mean by the length of a vector, or the angle between two vectors, or when two vectors are perpendicular. For example, think of the vector space Pn, polynomials of degree less than or equal to n. What does it even mean to say to refer to the length of a polynomial? I mean, it's not really clear. So we can't really hope to match up an inner product in general with some pre-existing notion of these geometric things because we don't typically even have pre-existing notions of these geometric things in other vector spaces. But what we can do is actually use an inner product to define these quantities. So rather than hoping that some inner product matches up with what we might mean by length of a polynomial, instead we'll use an inner product to define length of a vector in some vector space. So if we have an inner product on any vector space, we can define the length of a vector to be the square root of the inner product of the vector with itself. Of course, for this to make any sense, the inner product of the vector with itself, we need that to be greater than or equal to 0, because otherwise we're taking the square root of a negative number, which who knows what imaginary length means. But every inner product will always satisfy this property because this is just being positive definite, which is something that we require of inner products. We can define what we mean by a unit vector. Now that we've defined length, or often in abstract vector spaces, instead of length, we speak of norm or magnitude of a vector. But now that we have a definition for the norm of a vector, we know what we mean by a unit vector. A unit vector is just a vector that has norm 1. The distance between two vectors is just the magnitude of their difference, right? This is definitely the case for Rn, because, right, if we have two geometric vectors in Rn, the distance between these points is the length of this vector, but this vector is v minus u, or u minus v is going the other way, but either way, whichever way this vector is going, its magnitude is the distance between these 2 points. And so that we can define the distance between two vectors just as the magnitude or the norm of the difference of the two. We can tell when vectors are orthogonal because we can just say that they're orthogonal when their inner product is 0. So I should be careful. It's not that we can tell when two vectors are orthogonal by checking this. What we're doing is defining what it means for vectors to be orthogonal in this inner product space. And then finally, we can define an angle between any two vectors just by doing the same thing as we do in Rn. You take the inverse cosine of the inner product of u and v over each of their magnitudes. There is one caveat here, which is in Rn, we know that this quantity is always going to be less than or equal to 1 and greater than or equal to minus 1. So to be able to take inverse cosine of this quantity, it does have to be between minus 1 and 1. In Rn, the Cauchy-Schwarz inequality guarantees that this quantity is always between minus 1 and 1. So I guess what we need in the general inner product situation is some fact that corresponds to the Cauchy-Schwarz inequality. Just to remind you, the Cauchy-Schwarz inequality says that in Rn anyway, so let me write this with a dot product. In Rn, the Cauchy-Schwarz inequality says that the dot product, the absolute value of a dot product is less than or equal to the length of u times the length of v. Okay? Well, it turns out, I won't do this, but it turns out that you can actually prove this inequality only using the algebraic properties of the dot product that we require of any inner product. So the proof that proves the Cauchy-Schwarz inequality for the dot product actually proves it for any inner product. So, and again, I won't prove that, but it's not that hard. I just don't feel like it's necessary. So for any inner product, the absolute value of u inner product v is less than or equal to the product of their norms. And this, right, if you just move these over here, it says that the absolute value of u inner product v over magnitude of u, or norm of u times norm of v, is less than or equal to 1, and that means that this quantity is always between -1 and 1, and so it's safe to take inverse cosine of it, and so we can use this to define an angle between two vectors. All right, so for any inner product space, since we have an inner product, we can use the inner product to define geometric quantities. Let's look at a few examples. So in the space of continuous functions from 0 to 2 pi, let's find the norm of cosine of x. So remember, the norm of a vector is the inner product of the vector with itself. And of course, in this context, in this vector space, vector means function, continuous function. Sorry, I need a square root here, right? Because the norm is the square root of the inner product with itself. So we need the square root of, and then this inner product is the integral from 0 to 2 pi of cosine of x times cosine of x. So that's cosine squared of x. And so this is sort of a typical Calc 2 kind of integral to have to figure out. We'd need to use a trig identity. So cosine squared is the same as 1/2 1 plus cosine 2x. Okay, and then when we do an antiderivative, we're going to get, let's see, move that 1/2 outside. We get an x plus 1/2 sine 2x. And then we have to evaluate at 0 and 2 pi. When we evaluate at 0 and 2 pi, this term, the sine term, goes away. We get zeros everywhere. So the only term that survives is when we plug 2 pi in for x. So then we get 1/2 times 2 pi, so that's pi. Oh, and I forgot, I stopped writing my square roots. I need square roots. Okay, so the norm of the cosine function using this inner product on the space of continuous functions from 0 to 2 pi is just the square root of pi. So just as a follow-up, this means that the function 1 over square root of pi times cosine of x is a unit vector in this inner product space, continuous functions from 0 to 2 pi, because by dividing cosine by its own norm, you get a unit vector. All right, as another example, let's see what is the angle between sine of x and cosine of x in this function vector space. So to work out this angle, remember, to define angles between vectors, we calculate inverse cosine of the inner product over the vectors times their norms. So we know the norm of cosine already. It's square root of pi. And it probably won't surprise you to discover that the norm of sine is actually the same. If you run through this same calculation, but with sine squared instead of cosine squared, the only thing that changes is this plus turns into a minus, but this plus didn't affect the result of the calculation. So the norm of sine is still square root of pi. So to do this, all we need to work out now is the inner product. So let's calculate the inner product of cosine of x with sine of x in this inner product space. So this is the integral from 0 to 2 pi of cosine of x times sine of x dx. Of course, we're going to need a trig identity to work this out. This is the integral from 0 to 2 pi. So sine x times cosine x is 1/2 sine 2x, I believe. Okay, and so when we integrate, we get, I guess, minus 1/4 cosine 2x from 0 to 2 pi. But then when we plug in 0 and 2 pi and then subtract, we just get 0. So actually, cosine and sine are orthogonal. In this vector space. So that's maybe a bit of a surprise. As we'll see, it's nice to have orthogonal functions in this kind of vector space, because then you can do everything that we usually do when you have a bunch of orthogonal vectors.